Alright everybody, welcome to another wonderful math video, this time on section 5.4, covering two more segments that we find in triangles, medians and altitudes. So let's get started. First of all, first one we're going to talk about is a median. What is it? Well, it is a segment going from one vertex in a triangle to the opposite side's midpoint. So, if we look at the picture that's just below down here, we can see the blue lines are medians. For example, here's one that starts at point C, goes across the triangle, and then lands at point D. And you can see that AB is split in half by D. So, that makes CD a median. And you can also see that since there are three vertices in a triangle, that means that there are three medians that we can make in any given triangle. We start at each vertex, and we go to each opposite side's midpoint, and that's how we make them. The medians of a triangle are concurrent. What does that mean? Concurrent means they all meet in one point. And maybe instead of in, we should say at one point. If you take three random lines, they're not always going to meet at one place. But if they do, we can describe them as concurrent. And the point of concurrency, that would be the place where they all meet. For medians, the place where they all meet is called the centroid. So there's that. Now, medians and their centroid are sort of special in that they always have a relationship between their lengths. So if we look in this picture, for example, the one that's down here, let's make this a little bit bigger, not exactly the scale, and we're going to focus on one median in particular. So here's A, here's B, here's C. Let's focus on BF, that median. There's F. The idea is that this is the same length as this. I'll draw the other medians in because we kind of need them to show what's going on here. I remember this isn't exactly the scale, but doing the best I can. There's our centroid. So the whole idea here, as it says in this theorem, the congruency of medians of a triangle, if you look at any particular median, it's going to be split into two segments by the centroid. There's the first segment, there's a smaller one. One is always bigger than the other. And actually what we know is that the bigger segment is always going to be 2 times the size of the smaller segment. So let's call the centroid P as they do. What that means is that BP is 2 times the length of PF. You could do the same thing with the other medians, but it's always going to be true. A median is split into 2 places by the centroid. One is always twice as big as the other. So we can use that to our advantage, like in this example. In our ST, Q is the centroid and SQ is 8. Find QW and SW. So, again, if we're told that SQ there is 8, we can see that that's the bigger of the 2 segments. And like I said, and like we know from this theorem, we know that SQ is going to be twice as big as QW. So that tells us immediately that QW is 4, half the size of SQ. And if we add them together, to get SW, 8 plus 4 is 12. So that's all we need to do for that problem. So that's what medians tell us. So just remember, a median is a segment that starts at a vertex and goes to the midpoint of the other side. This is different from a perpendicular bisector, which starts at the midpoint of a side and then just sort of shoots up directly so that it's perpendicular to the side that it's on. It doesn't have to go through a vertex like a median does. So that's something to consider. All right, altitudes. An altitude of a triangle is a ray, actually a line we'll say, going through a vertex that is perpendicular to the other side, really the opposite side. Again, since this is starting at a vertex, there are going to be 3 of them in or around the triangle. And they intersect at a point called the orthocenter. Ortho is a prefix that means straight, which is why your orthodontist straightens your teeth. So the reason is because these are perpendicular lines, they kind of look like they're sticking straight out of all the sides. So down here, we have a few pictures of altitudes. Both of them are altitudes from Q down to line PR. Notice in this triangle, we have our altitude starting there. The side opposite from from point Q, is PR down here. So to make our altitude, we just draw the line straight down. We get our right angle. There it is. The second example over here is a little bit different. Here's PR, and here's point Q. If the altitude were inside the triangle, we wouldn't be able to make a perpendicular line. So this is going to look kind of strange, but the altitude from Q to PR this time is actually this blue line right here, going straight down outside of the triangle. The reason being, for us to be able to make a perpendicular line to PR, we kind of need to extend PR out this way so that we can make the line from Q extending straight down. Now, PR doesn't change length. It's the same segment it was. What you need to realize about altitudes is that they will not always be inside the triangle. Sometimes they go outside of the triangle. And that's what's happening in this example. That happens basically when you have obtuse triangles. With right triangles, you can have altitudes that actually fall on the triangle, and with acute triangles, they're going to usually be inside. So, again, this is a little bit different from any given perpendicular bisector, because while this line segment is perpendicular, and it is perpendicular to a side, it doesn't have to fall in the midpoint of a segment, and again, it's starting from a vertex, unlike perpendicular bisectors. So that's a big difference between them. So, brings us to a few problems that we can look at. These would be good things for you to consider. I'll start you out with a few of them, and if you want to try a few others and ask whether they're right or wrong, feel free to. So for example, the median of a triangle is always, sometimes, or never the perpendicular bisector. Well, the answer to this one we can figure out by trying to investigate some triangles. For example, if we look at an isosceles triangle, let's say that we want to make the median from this vertex up here. Well, that's just going to fall straight down the middle if this is an isosceles triangle, because we're starting at this vertex up here, and then we're going down to the midpoint of the opposite side down there. But if this is really an isosceles triangle, these are also going to be right, which makes that also the perpendicular bisector. But if we drew that triangle slightly differently, let's say that this side was shorter than this side, it wouldn't work out the same way. So this is a sometimes case. And, you know, it might be a good idea to try thinking about the rest of these on your own and see if you can think through them. And the thing you got to remember is that it's going to be true in some cases sometimes, but not true in all cases. Sometimes it will be true in all cases. Sometimes it'll never be true. So try some of those out if you want to. It would be good practice, if anything. This one, perpendicular bisector, median, or altitude. Well, you just have to examine what's going on around here. Remember, a perpendicular bisector cuts a segment in the middle and forms 90-degree angles with that side. So if we look at 10, we have two equal sides. It's being cut down the middle. There's a right angle. This is a perpendicular bisector. Is it a median? Yeah, it is. It's starting at a vertex and then goes down and cuts this side in half. So it's also a median. Is it an altitude? Yes. Starting at a point, going down to there, and making a right angle with that part. So it's also an altitude. In fact, perpendicular bisectors kind of are the, if they're going through a point, as it is in this case, combination of a median and altitude as well. Number 11, we have a right angle here, but for this to be a perpendicular bisector, we would need the right angle to be happening over here. And also we would need it to be cutting the shape in the middle. So it's not a perpendicular bisector. We see that this segment's coming from this point. It's not cutting the opposite side in half, so it's not a median. And it's not coming into the other side at a right angle over here, so it's also not an altitude. So this is none of them. And this one over here, number 12, well, we don't see any right angles, so we can't do anything with perpendicular bisector or altitude, but we do see that the line segment starts at B, goes to D, and cuts AC in half, making this a median. So, with these problems, you're going to do similar thoughts. It's kind of like the ones that we just did up there, but they're giving us specific information. For example, for number 17, they tell us that YW is perpendicular to XZ, which means that we have these right angles forming. Since we have a line starting at a vertex and going down and being perpendicular to the opposite side, we can say for sure that this is an altitude, but we don't know if XW and WZ are congruent, so we can't say that it's a median. Let's do one more of these, and then I'll end the video because we're getting close to time. XYZ is congruent to ZYW. XYZ is congruent to ZYW. I think this is a typo. This should probably say XYW is congruent to ZYW. So those two are congruent is what we're told. Well, the only thing that we can get from that really is that makes YW an angle bisector. I think the sheet was written with a typo at the beginning. So it should be XYW is congruent to ZYW. That means that this angle here is congruent to this angle here, which means that YW is splitting it in half, making it an angle bisector. So you're going to get more practice with this type of question on the homework, and please feel free to ask questions if you're getting stuck with them. But being able to tell the difference between these four segments, the four segments being perpendicular bisector, angle bisector, median, and altitude is going to be important, and sometimes things are more than one of them. So please, if you're feeling lost on this topic, ask questions in class. Make sure you get it. That's about it for this video. We'll be back with 5.5 coming up. So, see you there.